Okay, so the Mulliken electronegativity. The definition of the Mulliken electronegativity is based on the idea that ionization energies and electron affinities are nothing more than ways of expressing how efficiently an atom holds on to electrons. And in a way, we are looking at how good they are at attracting electrons. So Mulliken kind of saw this as a means of kind of averaging out those two components, the first ionization energy and the first electron affinity, and using some correction factors to look at the connection between electronegativity and those two values. And he found out that this equation gives you a relatively good way of experimentally coming up with these electronegativity values. But since electron affinity is making an appearance in the equation, and I showed you in previous videos that approximating the electron affinity wasn't really all that good of a process, what I'm actually going to use the Mulliken electronegativity is as a means of finding out the electron affinity via approximations. And that is to say that if you subtract 0.19 from both sides and divide it by 1.97 times 10 to the negative 3, you end up with the summation of electron affinity and ionization energy. Subtracting the ionization energy from both sides isolates the electron affinity. And if you divide 1 by 1.97 times 10 to the negative 3, that's the same thing as 508. So if you multiply 508 by the electronegativity minus 0.19, and from that you subtract the ionization, the first ionization energy, you yield the electron affinity. And this is a better way of actually approximating the electron affinity. Although, mind you, it's best if you do use the experimental values of ionization energy and electronegativity to find the value of electron affinity. You can still use the approximations. The value still will have some error, but nothing as bad as what you saw before. That's when using the Balmer-Slater approximation. Okay. The last thing to be said is that the first ionization energy and the electron affinity are both going to be in kilojoules per mole. Electronegativity doesn't have any units, so you don't get any units from that, but the 508 is what gives you the kilojoules per mole, even though I'm not showing it in the equation. Now, with all that in mind, I just kind of want to summarize all of this stuff. I know I didn't give you an example for the Mulliken electronegativity, but it's very similar to what we've been doing in the remaining videos preceding the Mulliken explanation. But what I want to kind of show you right here is a summary of the different trends that we have observed. When looking at the periodic table, we have examined what happens going from top to bottom and what happens going from left to right. And we've looked at four main parameters. We looked at the radii, whether it was atomic or ionic. We looked at the ionization energy. We looked at the electron affinity, and we looked at the electronegativity. And what you basically saw is that going from left to right, the radii tends to decrease because of the effective nuclear charge. But the ionization energy, electron affinity, and electronegativity, they all increase. And going from top to bottom, what you see is that there's an increase in atomic radius because you're going to higher energy levels and you're increasing the size of the atom. But the ionization energy, of electron affinity, and electronegativity, they all decrease as a result of the fact that the atom is increasing in size. And this kind of tells you that the radius is giving you the opposite picture. It's inversely related to the effective nuclear charge, whereas the ionization energy, the electron affinity, and the electronegativity are directly related to the effective nuclear charge. So the lower the effective nuclear charge gets, the lower the ionization energy, electron affinity, and electronegativity will get. But the radius will do the opposite. In addition, I have shown you 5 different parameters that you can actually calculate using the using the effective nuclear charge of the element. So using Slater rules to approximate the effective nuclear charge allows us to calculate each one of these values. And each one of the parameters here has an equation associated with it. I don't expect you to memorize these equations. In fact, when it comes down to exams, I will provide you with the equations, because even I sometimes have trouble remembering some of the equations, so I don't expect you to remember them. Although, as you might have gathered from our discussion so far, the Bohr approximation for the atomic radius and the ionization energy are probably some of the most important equations out of the five. But these five equations can be applied in much the same way. And once again, the electron affinity is better approximated by using the Mulliken version of electronegativity. So you need to know the electronegativity along with the first ionization energy to determine your electron affinity values. Okay, so with this in mind, I basically will end this lecture right here. And I expect that you guys will have a lot of questions because this is a topic that doesn't necessarily get covered in general chemistry, at least not in the regular textbooks, but I think it's a very important topic and it adds a much needed extra layer of knowledge to the idea of periodicity. So for better or for worse, you have learned this with me, and hopefully in due time you get to understand and appreciate the subtleties of this process, as painful as it may be at the given time. All right, so I'll see you on the next series. Bye bye.